Hey, welcome everyone. This is Code Raw, new day, new video, and as usual, today we're gonna do some lead code problems for the new ones. This is Code Raw. We do lead code every day until I get a job or internship, or not lead code. We code every day actually until I get a job or internship. Those are my social media account. Don't forget to follow me on them. This is my GitHub, and you'll find in the YouTube bio my LinkedIn, my GitHub, my Instagram, and recently we opened up a Discord server. You're all free to join it. And without further ado, let's go to the read code problems. So, uh, so actually, we are in we are practicing the 75 lead code problems. We did all those. Yeah, and now we're gonna deal with the bit manipulation problems. So I really don't know anything about them, so I'm gonna simply discover it and let's go. So okay, let's search about the bit manipulation. Okay, so bit manipulation. Let's go to this. Okay, so competitive programming, bit tracks, table of contents, compute XOR from one. Okay, so the problem can be solved based on the following observations. Say n modulo 4, the XOR value depends on the value of x. Okay, so x equals 0, then the answer is n. Okay, x equal 1, 1, then answer 2, n plus 1. Mm. Okay, so if n modulo 4 equal 0, then return n. If n 2. But why is that? I didn't understand. Then we're gonna simply count number x more than or equal. Okay, so we count power 2 to count of 0 bits. Unset bits while n, if n. Okay, so what is this? I'm really not understanding anything. Okay, so I'm gonna simply search on YouTube. Okay, so wait. This one is okay. So let's go with this. Okay. I'm gonna write 0. 1. 0. And 2. And write 1. Okay. Yeah. Okay. Okay, so the to find the negative number, like the sum of those two has to be 1 followed by all zeros. Okay, so 1, 1, 0. So I'm gonna sum this and this. I'm gonna 0, then 1, 0, 0, 1. Okay, so 1. Oh, okay, 1, 0, 1. Okay. Hey, thank you, man. Welcome stream. Okay. So 0, 0, 0 are gonna be all zeros. And 1 in the sign bit, like, okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7. Okay. Okay, so what is this? Shifting. Okay, so if we do a right shift, we're gonna move the 1 into the trash and then copy all the remain. And if you want to do a left shift, we're gonna put this into the trash and then copy all this into the copy the remain. Oh, is this what I welcome stream ولا شكرا وينك Okay, so this number is multiplied by 2 and this divided by 2, but yeah, minus 1 because it's pair actually. It's not pair.
That's what a left shift and a right shift generally do. Now, some of you might be wondering, what happens on a negative number to this sign bit if we're doing a right shift? Does it shift with the number or not? And that's an interesting question. And that's where we get into logical versus arithmetic right shifts. Let's consider the number negative 23. In a logical right shift, we do what we would logically think that a right shift would
Okay,
do.
so do.
We move everything
Yeah.
except the sign bit over.
So
This gets us this weird
in this case we divide by 2, and in this we multiply by 2.
value of 116, which doesn't really seem to have any particular relationship to the number negative 23. The arithmetic right shift operates slightly differently, but in doing so preserves an arithmetic relationship between the original number and the new right shifted number. What the arithmetic right shift does is it shifts everything over by 1, including the sign bit, but then it fills in the sign bit with the original sign bit instead of what a 0 as in the logical right shift.
Okay.
The resulting number is negative 12, which does still bear that sort of that divide by 2 relationship, except that with negative 23 divided by 2 is negative.
Say my name, please. Ahmed Shakro. Welcome to stream. Welcome to stream, man.
11.5, so we're rounding to negative 12 this time. So now we're on to our final topic, using masks to do things like getting a bit, updating it, things like that. First, let's review some of the basics. When we AND 2 bits, we get a 1 only if both of those bits are 1. When we OR 2 bits, we get a 1 if either of those 2 bits are 1. And when we do an XOR, we need exactly one of those 2 bits to be a 1. If both are 1s, we get a 0. So now let's turn to how you get a particular bit in a number. So how do we figure out if, say, this bit was a 1 or a 0? Well, if we create a mask or just a number that has a 1 only in that one bit, and we AND it with the original number, that'll indicate whether that value is a 1 or a 0. Because if there's a 0 there, the whole number will be 0. Otherwise, it'll be something bigger than 0. So that mask can be created by taking 1 and shifting it over to the left by I spots. So to figure out if the ith spot is a 1 or a 0, we just compare x, do an AND of x with that mask, and say, does that not equal 0? Now, what about setting the ith bit? Well, we can do a very similar thing. We create actually the exact same mask, and we just OR it with that original value, and then it'll make sure that that ith bit is set. Now, what about clearing the ith bit? Well, that's a little bit trickier, but still.
Okay, so well, like we're gonna search about the keyboard. Okay, I'm gonna search about the syntax or something. Okay. Is it the same thing? Okay, count number. Oh, okay. So if I really didn't understand the example. Okay, so say x and the XOR value depends on the value of x itself. On the value of x. So x equals 0, then the answer is n. Okay, so x equals 0. What is the number that's modulo by 4? That will be 0 or 4. Why? Why this is not? The answer is n. Okay, is n. x1, the answer is 1. 1. The XOR value. Hey brother, hey, welcome stream, man. Thank you. I'm fine. How are you? How's your day? Oh, I want to see another one. So all about manipulations, but we can start with manipulations sample. Okay, so let's call this. Okay, so I know what is a bit. Divide this one by 2. Okay. 25 reminder 1. Okay. I know this. So do I have to go to the examples of the LeetCode problems and we're gonna like learn by doing problems? Okay, so ways of organization notes. Okay, let's see that. Oh, this useful. Okay, so we're going by to the types comprising bytes like this. Float, double, even instruction. This deeper will important with this operation with bits are used in data compression. Data is compressed while converting one form to reduce space. Exclusive or encryption. Algorithm to encrypt in order to encode decode compressed file. So we all know that 1 byte compressed of 8 bits. Any integer or character can be represented using bits in computer, which we call it binary form. Okay, so contains only 1 or 0, or in its base 2. Oh, alhamdulillah, man. Or in its base 2 form. So 14, it's 1110 in the base of 2. Okay, so this is easy. For characters, we use ASCII representation. Okay, which are the form integer, which again can be represented with okay, so bitwise operator. There are different bitwise operations used in the bit manipulation. These bit operations operate on the individual bits of the bits pattern. Bit operation first can be used to optimize complexity. Some common bit operators are not. Okay, so bitwise not is an array operation. Flip the number. Okay, if the 0 to be changed 1. Vice versa. Okay, so this the note. Okay, so every one will be converted into a 0. Okay, and I know the and. Okay, and 1 and 1 will be 1, 0 and 1 will be 0, and then 0 will be 0. Okay, or I know the or, the XOR. Okay, the XOR 1 and 1 will be 0, 0 and 1 will be 1, 0 and 1, which is the inverse of or. Okay, left shift. We're gonna left the number to the left. Okay, so the shift operator is a binary operator which shifts some number of bits in the given bit pattern to the left and append 0 at the end. Okay, so left shift is going to multiply the bit pattern with 2k. Oh, so 1 left shift by 1 is equal to 2, which is 2 in the power of 1. Okay, so 1, 2 will be 4, which is 2 in the power of 2. Okay. Okay, I get it. Right shift is operated by we shift some number of bits in the given pattern the right append 1 right shift to divide bit by 2k is equivalent to divide the bit patterns with 2k. So 4 1 equal to oh, so we divide by 2 here, 2k k bits. We have 1 bit, so we're going to divide by 2 by 2 multiplied by 1, which is by 2. It's like multiplying by 2 and divided by 2. Yeah, Okay. Um, How to check given number is a power of 2, which is the left shift. Consider if n is the power of 2, sample solution to this problem is to repeat divide n by 2. If n is even, we end up with 1, then n is power of 2, otherwise not. Okay. So there are special cases also. If n equals 0, then it's not power of 2. Let's go. Okay. So if x equals then we're gonna sample, then we're gonna divide until we can't actually. So and then we're gonna return 1. Okay. So our function return true if x is power of 2, otherwise false. Okay, so let's try 6. Okay, so 6 2 is 0. We're gonna divide it, which is 3. And then 3 modulo 2 is not 0. So I'm gonna return this 1. How shall we return the x? Return x equal. Oh, this is false, huh? Yeah. If we have 3 here, this is false, so it's gonna return false. X doesn't equal 1. Okay. So the complexity of this is O log n. So the same problem can be solved using bit manipulation. Consider a number x. Oh, so this is a normal code. Consider number x that we need to check for being a powerful 2. Now think about the binary representation of x minus 1 multiplied by, okay, x minus 1. X minus 1 will have all the bits same as x, except for the rightmost one in x and all the okay, so 4 equal 1 0 0 in the base of 2. X minus 1, which is 3, will be 0 1 1. Can be obtained simply flipping all the bits. Oh, to the rightmost. Okay, so we flip it here, we flip it. Oh, okay. Also include the rightmost one. One thing about x and x minus 1, x and x minus 1 have all the bits equal to the x, except for the rightmost one. Like how? This is 0 0 and this is. Okay, so the rightmost is here. Okay, so it's different. Those are equal. Like the sum of them are equal. Okay, so those are different. Those are different. We can do this by checking if the binary number contain only one bit 1. Okay, so let's see the example. So 4 equal 1 0 0, the base of 2, x minus 3, x and also the operation x, the operation and. Okay, so this will be 0, this will be 0, this will be 0. Okay. 6, this will be 1 0 0. X will check if x equals 0 and we'll check if x is the power of 2. So return x and then okay, good. So count the number of ones, like does it longer? Okay. So what is the time now? It's 24 minutes. Okay, let's just revise a little bit and then we'll go to the problems. Okay, so count number of ones in the binary representation of the given number. So the basic approach to evaluate the binary form of a number is the reverse on it. Count the number of ones, but this approach takes log 2 of n of time in every case. Okay, so it as to get a number that's binary form, we have to divide by 2 until it gets 0, which will take log yeah. So with bitwise operation we can use an algorithm whose running time depends on the number of ones present in the binary form of the given number. So this algorithm is much better. So what running time depends on the number of ones present. Okay, so as it will reach to log n only in worst case. Okay, so while n equal n minus 1 count plus plus. Oh, so like it's real time. Why this as a percent of the previous the relationship between bit 6 and so as in x and something rightmost one and bit right to it are flipped. Yeah, so this is those are two flipped. Okay. Okay. Is this like in the in all cases like x and x minus 1? Oh, okay. In all cases, all flipped. Okay. And store it in x will reduce, then perform reduce it to a number contain number of ones, and it's binary form. Okay, less than the previous state of x, thus increasing the value of count in each iteration. Okay, so let's just like draw it. Okay. Okay, so okay, so what I am supposed to do? What the fuck? Scrum Master revision. Welcome to stream. في بالك انا منكم توا. Yeah. Okay, so tomorrow I have a exam actually, and I'm not. No, man, I just want another project. Like, why is this not working? And I'm not revising actually. Section the yeah. Okay, so more important new skills bro. Okay, so like if we have as the algorithm said, so I have like 6. What is 6 in base 2? So 6. Let's make this thinner. So 6, I think it's not 1, 2. It's 1, 1, and 0, and 5. 5 will be 1, 0, and 1. Okay, so the relation between x and x minus 1, that we're gonna flip the rightmost and the 1 behind. Okay, so the relation will be okay, so how we're gonna run this? Okay, so while n count 1, while n, which is while 6, n will be n and n minus 1, which will be 6 and 5. So we're gonna run through this. Count plus plus, we're gonna count 1 and 1. This is it. So we're gonna return 2. Okay, for example, 23 initially count 0. Now n will change to n minus 1. Okay, then n will be which will be which is equal to 22. Therefore we'll change to 22 and count to 1. As n minus 1 will be 21, and then n and then minus 1 will be, which will be, okay, which is equal to 20. Therefore n will change to 20 and count 2. Okay, 18, as n equals 0, the loop will terminate gives the result 4. Okay, the number of 1 present in the binary form of the given, which is 4 number. Okay. Okay, so the complexity is k, where k is the number of ones present in the binary form. Okay. Like, can we do the lead code now? I think we can. Okay, so is it here? Okay, so counting bits. Oh, this is the example we're doing it right now. Okay, so n equal to output 0, 1, 1. Okay, so given an integer n, return an array n of length n plus 1 such that for each I, the number of ones in the binary representation. Okay, 5. Oh, okay. But what? 2. What's this? Okay, so 0 is the number of ones in the binary representation of I. Oh, okay, so this is 0, so it will be 0, 1, and then the 2 will be 1, 0. But why did he print it? Why did he print it 1? Oh, like, is this the sum of it? Like, okay, so this 3, 2, and then 2 is the number. How we're gonna do it? It is very easy to come up with the solution runtime. Okay, I'm really new to this thing and I really don't know. We're gonna do a for loop. I think no, because he want to make a n log n. Yeah, we can make a for loop. Is the count of number of ones for each number from 1 0. Yeah. Okay. So here is 2 ones, so he's gonna write 2. Okay, so I think this is the same example as this. While n, we're gonna count. Like this gonna give us the count of this. Okay, so let's just put it aside. So n equal 5. So those are number from 0 to 5, and for each number we're gonna count the number of ones. Okay, so I think I'm gonna make a list of this. Okay. This will be while n. Okay. I think I get it. Like. So now I have n. So okay, so. Okay, Okay, let's initialize g equals 0 while g is lower than n. Then we're gonna append it to the list. Okay, so I'm gonna make the final list. L dot append. Now we're gonna append the numbers, every number. Okay, so L dot append g, and then so we can also count one using while x count plus. Oh, okay, so x right shift 1. Can we? Okay, so I'm gonna try this. So count 1. Okay, ones. Okay, so count number of ones. Is there like another? Okay. Okay, so I'm gonna try try this code, and then I'm gonna go to yours. Okay, so while while n like, okay, you know what? I'm gonna make another loop. Do not like. No, it's gonna be a nested one, and I don't want it to be nested. Okay, so while n but this it's an infinite one. Okay, so no worries. So like I want to append it and count in the same time, or can I like append? Okay, so I'm gonna make it twice. Okay, so for I in, or like for num in L while now I'm gonna start the while. Okay, so while num num will be num and num minus 1, and then count will be plus equal 1. Oh yeah, it's a clever idea actually. Okay, so oh okay. Oh okay, so we don't have to do it. Okay. So for then we're gonna make a nested loop if we count and then append. Do we? I think we're gonna make a nested loop. Or we're gonna like go I think if we like count the zeros or the ones and then append, we're gonna like make a nested loop. And I want the time complexity to be like lower, you know. Okay, so we're not gonna append the number itself. Yeah, man. Okay. Okay, so I'm gonna make this 102, and then L dot append count. made this work. Okay, so I'm gonna initialize here, count to 0. What is this? Okay. Okay, so point num count plus 1, and count for each. Yeah, that's the idea. And then after all this, we're gonna return the app. Okay, so let's go. It's not num. Okay, so num. And here, after this, we're gonna increment. So to have this to be num equal 0. Okay. The thing, is it an infinite loop? Okay, memory limit exceed. Memory limit. Okay, so I'm not gonna append, I'm simply gonna print to see what's going on. So print count. Why is okay, so I'm gonna like try it once. I'm gonna simply try it on a one number and then okay, so bring this here. Okay. Okay, so what did he print? 0. It has to be like okay, so the number phones. It's the original number and that is in the loop, not num. Oh. Oh yeah, it's in here. It's in. Okay. So let's change it in and then let's see. Okay, so 1. Okay, so this is good. 2. Okay, so I think this is good. Okay, so I'm gonna make a for loop. Oh no, cannot. Like why this? Let's bring everything to its. Okay, so element count and num plus 1. Why it's infinite? So the algorithm is doing good. Do while n. While n. It needs to be in a list for each number. Needs to be in list. Yeah, so I append it in count. Output limit exceeded. Print count. One nums. And then append count and then nums plus one. What is going on? Okay. Mm. It's while n. But I'm like in every loop I'm telling all this and this and this, and it's fixed. It's like, okay, so I'm gonna follow you and see what is going. But then I'm gonna increment this or like what? Okay, so he only did one number, which is the number itself, which is n. But now I have to like if I make a for loop, I can do it. We're gonna make a for loop, okay? For num in range range 5, range n plus 1 actually, while y is not num, like count append count num plus 1, so I don't need this anymore, and then I'm gonna print this. Okay, I hope this work, hopefully. Okay, okay, so one 2 4 I think I have to like okay, here I'm gonna initialize count to 0. Okay, this is gonna work, yeah, it's good, that's good. Okay. Okay, the runtime is so long. Okay, let's see what others did. Okay, let's see it in Python. Okay, I really don't like understand this. Okay, so to understand solution, remember the following 2 points from maths. All whole number can be represented by 2n even and 2n plus 1 odd. For a given binary number, multiplying by 2 is the same as adding a 0 at the end. Oh, which is the left shift. Just as we add 0 when multiplying 10. Oh, okay. This is a good insight. Okay. So since multiplying by 2, just add 0, then any number and its double will have the same number of ones. Yeah. Likewise, doubling a number, adding or increase count exactly. Okay. So the number and its double have the same count ones, but the even one will be plus 1 because we added a 1 actually. Okay, thus we can see that a number will have the same bit count as half that number. Okay, so it's 50 minutes. Okay, so there's one. We iterate through a range of number and calculate each bit considering this one. For a range num, counter of I equal counter of I multiplied by 2. Oh man. Okay, sorry. I'm gonna skip it to go to the second problem, and then we're gonna return to it. Okay, so single number given a non-empty array of integer nums, every element appears twice except for one. Okay, so is the life is going good. Okay, so yesterday the like is it like cool to is it cool to take a rest like for 2 days? Is the stream going on? Yeah, okay, everything is good. Is it cool to take a rest like okay. The stream is live. Okay. We listening. Okay, thank you. Okay. So given an empty array of integers, every element appears twice except for one. Find the single one. Okay, so you must implement a solution with linear runtime complexity and use only. I forgot. I want to see like the uh, the uh, the complexity, not the complexity, the time complexity of this. Yeah. Oh, okay. So it's n log n, like he said in the description. So he wanted a solution with a n log n. Okay, so we're good. Okay, let's go back to this. You must implement only constant extra space. Okay, so constant extra space. Hmm. So nums equal to 1, so we have only one element who didn't like repeat, and then the 4. Okay. Okay, so how we're gonna do this? Hmm. Okay, do we have like no? Okay. I think there is no answer here. Okay. How generate all the possible subset of a set? Check if the ith bit. Like in the normal, in the normal. Okay. Subset of a set. Okay, I don't need that actually. Find the largest power of 2. Okay, so bit manipulation. Run run unique and repeating numbers in an array. Okay, so I don't really found two repeating elements in an array. Every element appeared twice. Okay, so I think you can loop through count each value. If the count is 1, you return it. No, this is the classical way. I think we're gonna use the bit manipulation thing, you know, because we're like we're working on the bit manipulation, so we have to use another approach. But welcome stream, man. Thank you. Okay. Where is the? Is this the same example? Okay, so I don't really want to see the answer. I just want to learn the approach, okay? 2153. No, not non-repeating. Not the two. Okay, I really don't know. Uh, I'm gonna search. We can maybe use two extra integer that hold the answer and like, is this in the bit manipulation approach or like the classic one? Because I really want to use the bit manipulation thing, you know? Go single number. No, coach F. Yeah, so is that like a. Okay, how do I make my single bits? Single number. We can repeatedly. Oh, we can repeatedly to a number set to 0. If the number return a new number, we know it was encountered once. Yeah, yeah, yeah. Yeah, that's good, but like, okay, so let's just search for another. Okay, so here is 4. Uh, okay, so shift operation. So one, we're gonna shift it by one. To solve this problem, according to the constraint, linear time complexity, we must be familiar with bit manipulation. Let's review. Yeah, I'm not familiar with it. Let's review some core concept. Okay, so we just move bit left, which means multiplying it by 2. Okay, by 2 because binary base 2. To move them to the right, to use the operation. And operation applied, done bit by bit. Okay, so we move them like or operation. Okay. Okay. How the fuck do you even get motivation to do it code every day? You know. Yeah. I really don't know how to get the motivation. Actually, welcome stream by the way, but I think because I like challenge myself in front of you. Like I wanna keep my promise. You know. So even if I'm not motivated, I'm gonna make a stream and like do it with my least energy, you know, not my least energy, with the energy I have today. So I'm really not always motivated, but I have to do it, man. There is no other ways. Welcome stream, by the way. Okay, so solution. The solution is not that easy to find. In a nutshell, we have to iterate over each bit of each number and check if each bit position if the sum is not multiple of 3. Why is 3? Okay. Now using this presentation. Okay, so 5, 6, 5 for each bit position. Let's sum the bits. Okay, so 1, 1, 1, 4. Okay. As we said above, let's check which sum is not multiple of 3. Okay, this is multiple of 3, this is not, and this is not. The sum of position. Hey, thank you, man, thank you. Uh, Thank you. Hey, welcome stream, man, thank you. I followed the lead code 75. So since I was streaming, I started like solving from this. So now I think I solved like I solved 46. Yeah, 46. So I follow this roadmap of lead code 75, and yeah. Okay, so let's go back to our. Okay, so the sum of the position 1 and 2 are not multiple of 3, so we have to see the bit 1 for each of these positions. It gives us 1 1 0. Okay, so if we fill this with 1 and 1 and then 0, we're gonna go 6. Okay, in Java you have to iterate. Oh, okay. Okay, so but how's this? And why 3? Why 3? Okay, so if we do the sum and the numbers who are not like divided by 3, we're gonna assign them to 1 and 1 and then 0. This number 110 will be the number not repeated. Okay, so imagine we have like, okay, I have to draw it. You're welcome, man. Welcome. Okay, so okay, so we have 6, 6, 5, and 6. Okay, so we already did this. Okay, so let's make this 5. Let's make this 5. So we don't have numbers. We don't have like single numbers. Okay, so the 5 it's 1 1 0. No, it's 1 0 1, and this 1 1 0, and this 1 0 1, this 1 1 0. Okay, so this is 0. This is 2 actually. I'm gonna make it 2, 2, and then 4. Those are not multiplied by 3, so 0 0 0. So we don't have. Okay, so let's put like 4 and then 5 5. Okay, so 1 0 1 and no 4 it's 1 0 0 1 0 1 and 1 0 1. Okay, this is 2 0 and then 3. Okay, so 1 0 0. This is 4. Yeah. Yeah, I don't know how it's work, but it work. But it works, man. Um, so the thing, okay, so if it's like 5, if this is 5, okay, so I'm gonna try just another example, the last one actually. So 1 0 1. Okay, oh, this is 3, this is 0, and this is oh, it has to be repeated twice. Oh, okay. So we cannot repeat any number like okay, so I'm gonna make 6 and 6. So 1 1 0 and 1 1 0. What about storing the frequency of each number in hash map? Yeah, we can make this. We can make this actually, but we are like working on the bit manipulation, so we have to use the bit manipulation approach. Hey, hello, welcome Steam. So I'm working on some lead code problems. So we are now working on the bit manipulation problems. We are now on the single number. Okay, so suppose we have 1 1. I'm gonna make 2. I'm gonna make 2. We're gonna make 5. Okay. So none of them is multiplied by it can be divided by 3, you know? It's not version multiply multiple of 3. Oh. Yeah, so we have zeros. This is false. We have to get 4. I really don't understand the thing here. Okay, so I'm gonna copy it and go to the chat and see why it's true, because I really didn't come up with a good explanation. What's up, Mohammed? The Korean guy like the idea from what I got. Hey, that's good. Maybe try my approach. Okay, so I really did. I guess it can work. I'll be meeting with him again tomorrow. Hey, that's good. That's good, man. Okay. Okay, so the provided method identifies a unique. Okay, so let's just see the explanation of ChatGPT of it. So the method analyzes each bit from 0 to 31 for 32 bit. For each position, it counts how many number is in the list that have specified bit. Okay, so module operation. Okay, since every number except one appears exactly 3 times, any bit that appears a number of times not divisible by one must belong to the unique number. Oh, okay. So this is because the unique number contributes bits exactly once. Oh, so this is why we divide by 3. Their bits 3 times, which cancel out the modulo theorem. Okay, so this is because unique numbers contribute its bit exactly once, whereas other contribute their bits 3 times. Okay, so this is the main idea. Bitwise assertion. So if the campus position is a non-zero, the bit at that position is part of the unique number. Result is bit shifting. So the variable position that start at 1, the least significant bit, and is left shifted. At the end, each iteration moves the next bit. Okay, code work through. So example, we have two. Oh, okay, but here I think it can be twice. Oh, okay, so I think this is not the right thing. But like just we're gonna modify this if count modulo 2. Okay, so I think we have something here. Okay, so I think I'm gonna make for rearrange. Okay, so I'm gonna make a result. What do you think, chat? I think this can work. Okay, so I'm gonna make result, which we're gonna return it and count bit position. Okay, so as he did bit position. And what we're gonna do? Range 32. We're gonna like you said, we're gonna go through the 32 bit positions. So for in range 32, we're gonna make count equals 0 every time, and then we're gonna make another for loop num in nums. Now we're gonna iterate through the nums. Okay, so if num and bit position, then we're gonna count plus equal 1. Okay, as the what? As the Nightbot said, don't forget to subscribe. Make sure that you are subscribed, man. If you want to see more content like this. So if it's 1 2 equals 0, so it's divided by 2, we're gonna make an OR. Okay, so that's it. Bit position. And then I'm gonna shift to the next position. So this is no, actually we're gonna make a 100k this year. Hopefully, man. Like this will be a dream, man. Okay, so we're gonna return the result as I said. Okay, I'm simply gonna. Okay, so this is school, this is school, this is school. No, not 1 million. Okay, so the result is good. Oh, okay. So, like, I used this example, but I simply modified this to be modulo 2 because we only have a number, it can appear max 2 times, not 3 times. Okay, so the result is good. 1 million? No, I think it's hard 1 million. Oh, the negative numbers. Oh, okay. Okay, we'll search on it. Didn't he included it? I think not. What gonna do with the negative one? Okay, so Chad said this. Okay, so if result 2 multiplied by so this is a so the output is very big, so if it's bigger than this, then we're gonna delete this because this the positive inverse number, you know. Oh, we cannot expand in block if just an if statement. Oh, the independent. No. Try returning instantly, learn to improve time. Learn nums equal 1. Okay. Yeah, the thing means left shift. This sign means left shift if we have if we have 1 1 0, so we're gonna take the this and we're gonna shift this, so it would be no, we're gonna take this. Okay, so it would be 0 1 1. Okay, you can use the failed test case without submitting again. Yeah, I forgot actually. Thank you, man. Okay, so the runtime is not bad. Yeah, it's not bad, but okay, and the time complexity. Okay, so I don't have like a lead code premium. Lead code premium, man. Okay. So is it like mine? Okay, so it's better. Okay, so this is like, oh, now it's 1 hour. It's 1 hour like. Alright, this was very nice. Hey, thank you, man. Okay, so now it's 1 hour, 17 minutes. I think I'm gonna end the stream here. Thank you, everyone. This was really nice lead code stream. Thank you again for the 1,000 subs. So we hit 1,000 subs like 3 or 4 days ago. Thank you again. Thank you for commenting. Thank you for following. Don't forget to follow me. Don't forget to connect with me on my other social media account. I would be too happy to connect with you and interact with you. Thank you, everyone. I think I'm gonna end the stream here. So as usual, we're gonna meet tomorrow in this time. Thank you, everyone. Hope you like this video, like this stream. Don't forget to subscribe. Don't forget to follow me on my other social media account. And see you tomorrow. Thank you.